Hello everyone, welcome to this series of lectures about machine elements design. Today we're going to discuss shaft design. We'll be looking into equations used to design shafts under static and fatigue loading. And as we'll see in the coming slides, it's not a straightforward process. We will have to use some kind of iteration. So we'll be using Newton Raphson's method to develop a spreadsheet or a coding program to calculate the shaft design. I'll be using spreadsheet, so I'll be sharing that with you. And I'll show you how we do some kind of iteration in order to reach an acceptable trial and error or an acceptable diameter based on an initial assumption and a calculated value. So now let's first take a look into what are some of the criteria or some of the variables that controls the shaft design. As we can see in this picture, you have different functions or structures being assembled or installed in the shaft. So let's go back one step. Why shafts are actually, why do we need shafts? Why shafts are mainly used? A simple answer to that is that shafts are used to transfer or transport power from one location to another. Okay, for example, what we see here, this is a pulley, so probably we have a belt here, maybe connected to another pulley that's connected to a driving motor that would rotate, and we need, let's say this is a gear, so this gear is connected to another machine, so we need to drive that machine using the motor that we see here. So this motor will drive the small pulley, and the pulley will drive the belt. The belt will in turn start turning and turn the pulley, the bigger pulley, which is connected to the shaft, and then the shaft will start turning. So how does the shaft turn as the pulley turn? We need to connect the pulley that we see here to the shaft using, for example, a pin. That's one method. So if you look from the top, if you're looking from the top side of the shaft, what we really have in this location here is the shaft, and then it has a hole. Or if you're looking from the side view, you have the shaft and then it has a hole, and that actually creates some kind of concentrated stresses there. And then you have this gear. We need to fix this gear to the shaft. Again, we can use a key. This is a Woodruff key. So that needs that you engrave some material here for the key to sit in, and you can see how it's inside both the gear and the shaft. So that's going to change the geometry and create some kind of concentrated stresses in the shaft. We need this gear, we need to prevent this gear or support the gear so that it doesn't move to the left or right. So to the left, we can build this larger diameter so it creates a seat for the gear to sit on. And this key will prevent it from moving to the left, both left and right, but we need additional support, so that's why we have this seat here. If you look to the right gear, the left side gear for you, we have this seat. Another method, instead of using the Woodruff key, is to use some kind of a hub with some bolts or screws. Sometimes we use snap rings, shoulders. So all these actually are gonna create some grooves, some holes, some keyways inside in the shaft, different diameters. And that what makes the design of these shafts a little more complicated than just a bolt, a static bolt. And then remember, those will start rotating, and that's what gonna create what we call fluctuating loads on the shaft, and that's the main definition for what we did when we introduced fatigue loading. So now, not only that we have to worry about all these concentrated stresses and loads, they're actually gonna start rotating and fluctuating, and that's going to create fatigue stresses and fatigue loadings. Okay, so this is another picture that shows some of the, sometimes we use locking nuts, so we need to create some kind of threads there, keyways, different diameters, step diameters, etc., holes, and so on. Okay, now the stresses that affect the design of shafts under static loading, not fatigue or fluctuating, are kind of simpler than fatigue. Now recall the factor of safety. In general, it was defined as the strength, which can be SY or SET, since we're only discussing static loading, divided by the maximum stress, which, let's assume we have KT times sigma prime. I'm gonna take separate loading, so I'm gonna mix bending with axial with torsion. Otherwise, if you have a mixed situation, then you will have to put the stress concentration factor inside your stress equation, the von Mises, for example, here. So you will have to use KT for axial or bending times sigma x squared plus KT sigma y squared minus KT times another KT, so KT squared sigma x sigma y, that's coming KT times sigma x KT sigma y plus 3 KT from torsional or shear tau xy all squared, all this under the square root. So we'll find the maximum stress from there and then we'll use it. So if we have only normal stress, such as tension or compression, or normal loading, so my factor of safety, N, will be equal, let's say we have ductile material, so it's SY divided by KT sigma N, where sigma N is equal to F over A, the force, divided by the area. Let's assume we're doing cylindrical, so the area is pi over 4 d squared, so if we substitute here pi over 4, so it's kind of SY times A divided by KT times F, so it becomes pi SY over 4 KT times the load F times the diameter squared. From there we can find an equation for the diameter if it's only under normal stress, and that's equal to 4 times the static stress concentration factor times the loading, the applied force, F times the static factor of safety. We can use N sub S since we're only doing divide by, we're only doing static so far, pi times SY under the square root. So that's my equation that we might use for designing shafts under normal stresses. The second type, we have shear stress. So the same way, N, the factor of safety, N. So let's assume we have a bolt, and then there's an applied force, F sub S, or just simply F. and we're only doing pure shear, so we don't have other types. So again, we'll have SY divided by KT sigma prime. However, notice that since we're doing shear, so I'm in this, so we have this as SY over square root of 3 KT tau XY. Now SY divided by square root of 3 is what we call the shear yield strength, SY sub S. But we'll keep it as SY just to see the square root of 3, or we can substitute that by SYS if we want to compare the form to the normal shear stress. We'll do the same. We'll substitute here F, the shear, divided by the shearing force divided by the sheared area, which is again pi over 4 d square. We'll rearrange the same way. We're gonna get the same equation. Now we'll use KT sub S because this has to come from torsional or shear, so either way we'll have an equation for the diameter, and it will end up as 4 KT sub S times the factor of safety times the load, the shear force F sub S, divided by times the factor of safety, the static factor of safety, divided by pi SY over square root of 3, or we'll just use SYS. And you can see it's the same form for those two cases, except the strength, of course, it's for shear yield strength. Over there we'll use the yield strength. The third case is bending stress. So how do we find the diameter of a shaft under bending? The same way as we did before, it's SY divided by, we're gonna skip that case, the discussion here, so we'll just assume it's KT times, since we only have pure bending, we're assuming that we only have pure bending. And recall what was the equation for pure bending, or the bending stress. It's 32 times the bending moment divided by pi d raised to the power 3. So we'll substitute this for sigma bending. So I'll have SY pi d cubed divided by 32 KT times the bending moment M Therefore, the diameter d based on bending stress will be equal to 32, the factor of safety, the stress concentration factor, times the bending moment M divided by pi SY. So it's actually very similar, it's very similar to this form, except now we have, instead of 4, which is coming from the area, it's 32. That's coming from my definition here. But so we have a constant stress concentration factor, the factor of safety, and then we have the type of load, or the type of variable that creates that stress. So here we have shear, so it's the shearing force. The first case, the normal, it's the normal force. Here we have bending, so it's the bending moment divided by pi times the strength. This one is cubed, so once you solve for the diameter, it would be raised to 1 over 3. The same way you can do torsional stress. We have the static, again we have SY divided by KT torsional square root of 3 tau torsional. Remember, tau is 16 torque times the torque divided by pi d cubed. So instead of 32 m, we'll have the same exact process there, except we'll replace 32 and m by 16 and t. So we'll have, and SY is SYS. If you take SY divided by square root of 3, So the diameter that has to overcome torsional stresses only is equal to 16. The factor of safety, Kt sub s, coming from the torsional charts, times the applied torque divided by pi sys, and again it's raised to 1/3 because it's pi d cubed. Okay, so these four cases are only when considering static loading, not fatigue loading. It's almost the same when you start solving for fatigue, except instead of having only one force, you start seeing the fluctuating force. So if you have bending, you're going to have M, instead of M, you will have MA and M mean. Instead of a torque, we'll have TA and T mean, and so on. Force, applied force, normal force, and mean torque, and so on. So these are the equations for the fatigue stresses for torsional and bending. And mostly when we design shafts, axial loads are very small and we kind of ignore them in addition to shear stresses. We have seen before when we compare shear to bending, shear is a very small fraction of the bending stress. So we will mainly focus on two things when we design for shafts: the bending moment and the torsional effects. And since we're talking about shafts, so usually they're round, so we'll be taking those special cases for round shafts. So I won't be finding I and J, the polar and the second moment of inertia. We'll actually be looking directly into those equations. So we can see sigma, for example, for bending, it's K at 32m divided by pi d cubed, except now I have two portions. I have the alternating portion, as we did in the fatigue stresses analysis, and we have the mean stress, and so on. If it's fully reversed, which means you have a shaft under a load, let's split this shaft above and below the center line. So we have A, for example, here. So in the first instant when you start, it would be under compression. If I'm only looking into A, this portion below, it's under tension. After 180 degrees rotation, it's still the same, so that's A here. So after 180 degrees, what we have is A becomes down here. The shaft rotated 180 degrees. Sorry, this is tension. So you can see point A, or which is the upper portion of the shaft, it will start fluctuating between plus and minus. This is fully reversed because nothing has changed in terms of the load. And we're going to have the fully reversed case, which gives you the mean value for the force, for the stress, etc. Torque, so always we have the mean value 0, and the amplitude, or the alternating portion, it's equal to the value itself, x max. So if we're doing bending, then m mean will be 0, the alternating portion m sub a will be equal to the maximum moment, and so on. And the same discussion can be done for the torque. So now how do we design the shaft diameter after introducing those four portions? We have the alternating moment, we have the mean moment, you have the alternating torque, and you have the mean torque, which gives you the alternating bending stress, the mean bending stress, and the two portions for the torsional stresses that you might have. So the first case, which is actually a special case, which we'll be using only for fully reversed bending and steady torsion. So the torsion, the torque applied, it's steady, it's not fluctuating. And we'll use the ASME equation, which is equal to this form that we see here. This form actually, it splits your, or it combines the fluctuating torsion, so we see it here, it's the fatigue stress concentration factor, K sub F, times the alternating portion, the alternating part of the moment. So that's the moment, and it's saying fully reversed bending, which means bending, the moment is fluctuating with time. So we have here, that's MA, and then M mean is simply 0. And that's why we don't have anything related to the mean bending. And then it says steady torsion, so what we have is just simply, if we look into the torque over time, it's just a straight line. It can be any value. If it's 0, then that's a very special case. But it's steady, so we only see this kind of like a static portion. And if you look into the stress over the strength, and then you have the factor of safety here, so this portion gives you the fluctuating part of the bending. And this part gives you the, like this portion of the equation, it gives you the static torsion part. Okay, and that's why it's this one is divided by the fatigue strength. Should say the corrected fatigue strength. And this one will give you the yield as dependent on the yield strength. Okay, again, MA is the fluctuating part of the bending moment. N sub F, it's now the fatigue factor of safety, or just simply the factor of safety. And divide by pi. If you look here, you have MA divided by strength, or torque divided by strength. So MA and T, they have the same unit. It's force times distance. Divide by the strength, which is force divided by area. So force over distance squared. So this will be distance cubed. So force with the force, and then you have square and then square root, so square it and then raise it to 1/2 so square and square with the square root, it cancels. And then we have cube, and then all that is raised to 1/3, so that's going to give you the unit of the dimension of a distance. So if you're doing SI, it's going to be in millimeters. If you're doing English units, it would be in inch, feet, etc. Okay, now let's recall what's K sub F. It's 1 plus the notch sensitivity times KT minus 1, whereas this is the static stress concentration factor, which we have special charts to pick these from, or we have equations. And this is the notch sensitivity. Also, we have charts and tables to get this value from. And we did this in the previous chapters. So we can use this equation now in the next to apply for the different stress concentration factors that we might see. Okay, and before I go to the general equation of the shaft diameter, let's recall what's the corrected fatigue strength or the endurance strength. It's equal to, first, the correction factor for the loading, the correction factor for the size, the correction factor for surface, the correction factor for the temperature, the correction factor for reliability, and all that multiplied by the uncorrected strength or fatigue or endurance strength. which we have tables for steel, aluminum, copper, and iron. Those two are ferrous materials, so we'll use Se whenever we do this, and those two are non-ferrous materials, so we'll use S sub F. Now, where's the challenge here? If you recall, C size, from its name, it's the correction factor for the size factor. So it has, let's say we're doing the English units, so it's 0.869 d to the negative 0.097 if it's under, let's say, bending, for example. Because if it's under fluctuating axial load, then C size is just simply equal to 1. Okay, so we need the diameter d in order to evaluate C size, in order to find Se, to plug it in my equation, in order to find the diameter. But wait a minute now, I just said I need d to evaluate C size, to find Se to find d. So it's kind of like a circle. I need d to find C size, and I need C size to find Se or Sf in order to find d. So it's kind of like a circle. Where should I start? And that's where the trial and error becomes handy. You're going to assume a value for d, you will evaluate C size, and then you'll plug it here in the equation and find your the diameter, calculated diameter, and then you will be comparing the initial guess, initial assumption to your calculated value. If it's too far away, and I'm going to be defining that tolerance, the difference between the assumed and the calculated value. If it's acceptable, then that's your design value. If not, then you have to repeat the iteration, you'll make a new assumption, and then you will do a new calculation, and it keeps going on. But before we do that, let's look into the more general equation, which is the fluctuating bending. So it's not fully reversed, it's not repeated, so it can be, but that's a special case, and fluctuating torques as well. So that's the equation. It has the 4 parts. It has the fluctuating moment, mean moment. It has the fluctuating part of the torque and the mean part of the torque. So the fluctuating torques and moments, this portion here, it gives you actually the fatigue portion of your design. It takes care of the alternating moments and torque. And this portion here, it gives you the static effects. And that's why, you know, it's divided by, or the strength used there, it's the ultimate, so it's kind of like a static, whereas this portion is divided by the fatigue or endurance strength. And the same way we have the stress concentration factor times the moment stress concentration factor from the torsional charts or equations times the alternating part of the torque, and then the same way goes for the mean. So now we see we have 4 different stress concentration factors. All that, so this big bracket, you will multiply it by 32, the factor of safety, divide by pi, and then to 1/3. Okay, so Kf is equal to 1 plus Q for bending. So now we're talking about bending, so I'll need to go to the bending charts and find that notch sensitivity times Kt, the static for bending for that structure that you're analyzing, minus 1, so you'll find your Kf, and usually this is equal to Kf mean, so the mean value for the stress concentration factor in most cases. But it can be different if you calculate a different value for Q. And then we have Kf, so it's the fatigue stress concentration factor from torsion, so it's equal to 1 plus Q from torsional curves or charts times, again, Kt from the torsional charts, and then minus 1, and this will give me my fatigue shear stress concentration factor. And the last one, which is under the mean, Kfsm, we will always take it equal to 1. So you won't even see it inside your equation, but this is the general form for your equation. Now, one thing that a common similarity between this one and the previous one is when it's fully reversed, and even the static. So if it's fully reversed and no torques, for example. So fully reversed bending, that means mm is 0, ma is there, it's equal to the maximum value, and then no torque. So what happens to your equation? We can see that the equation here, no torque, so this term will disappear, right? This term will disappear. Now no moment, so this term also disappears. So all this static portion, it's not there anymore. So what I have left is 32 times the stress concentration factor divided by pi, and then I have kf ma squared square root, because no torques, divided by sf, and all this raised to 1/3. Does this form look familiar? If you cancel these two, what happens? Square and square root, they cancel. So we will get 32 times the factor of safety times the stress concentration factor times the bending moment divided by pi strength. So now since we're talking about fatigue, so we have fatigue, stress concentration factor, fatigue moment, and fatigue strength, and all that raised to 1/3. It's actually exactly the same as the static equation for the diameter, which we derived before when we're doing this case. Except this is from static, that one is for fatigue. So this equation actually, and this one too, if you remove the torque here, so we have k at square root, they cancel each other, and then we have 32n times the stress concentration factor times the bending moment divided by pi times s, the strength, the fatigue strength. Okay, so again, we're back to what's SF? It's the same as we defined here, all these factors, and C size as a function of the diameter. So again, I need to make that initial assumption for the diameter, find the diameter, and then plug it in my equation to evaluate the endurance or fatigue strength, and then find the calculated value for D. Okay, so one method to do that, you can, for example, make an initial assumption for the diameter D. Sorry, let's go back. So you can make D, make an initial first trial 1, assume a value for D, evaluate C size, find the fatigue strength, plug it in your equation, and then assess or calculate, evaluate this. D will have D calculated 1. I'll just call it D calc 1. So if the difference between this, the calculated diameter, and the assumed diameter, if it's not small enough, if it's larger than a given tolerance, then you need to make another assumption. So this might take forever. You make another assumption, you evaluate C size SF2, and then you will get a new calculated diameter. And then you would go back and evaluate this delta D now again. So I have D calc 2 minus the assumed value, the second assumption 2. It's still larger than the tolerance. So should I increase or decrease my assumption? Am I too far away or what? So there's a method to solve such equations, and that's the Newton Raphson's method. Okay, so let's assume my big function, for example, it's this f of y, and then you would make your initial assumption, let's say P0. So we will plug that diameter in C size and evaluate the big function, and that's where we'll be here. And then in order to calculate, to find the root, we draw a tangent. So we're going to evaluate that function. So we'll draw a tangent and it gives me the solution, P1. So this is my initial assumption. And this is the calculated. And this is the actual root that I'm trying, or the actual solution that I'm trying to find. You can see I'm kind of far away, so the distance between P1 and P0 is far. So you started with 1 inch, you ended up with 10 inches, so it's larger than a given tolerance. And we're actually also far from the solution P. So we will do the second assumption. However, this method, it says take your calculated value and use it as your second guess, second assumption. So I'll use this P1 now. I'm gonna take the value that I calculated for the diameter. I'll take it, plug it in my equation. So I'll take it as my second assumption. And I'll solve, I repeat this process. So we will plug it in the equation and then solve. So we'll take the tangent for that. You can see now the distance between those two, it's shrinking, it's becoming smaller, and we're getting closer to the actual. Now if this distance is small enough, then you're gonna stop or you keep repeating. We'll take the new calculated value as my third assumption. We will evaluate the function again. We'll take a tangent until I'm too close to my actual solution. And we can see it here as well. So I'm starting with xn. I evaluate the function, and then we draw a tangent. We get this new value, and then we'll keep repeating that. We'll evaluate the function, take the tangent to solve for the root, and you can see it's converging. You have to be careful sometimes if your initial guess is kind of, it's sensitive on the initial guess depending on the function. So if this function kind of becomes a little flat here and you make your initial assumption here, you try to evaluate, once you try to find the solution, it's going to diverge because it's going to go to, let's say, minus infinite, so it won't like it. So there are a couple things that we need to do to refine my solution. That's one method, to use Newton Raphson's method, and that's what I'm going to use when building my spreadsheet to solve for that equation. Other methods are, we have some graphical methods to solve for this. We can we can say this is my y1, which is f of d. It's just simply f of d equals to d. f1 of d equal d. And this right portion, it would be f2 of d. It's equal to all that. It's all numbers except I have a diameter here. Now those two functions are equal, so if you're using a graphical method, then when those two functions, so this is f of d, y of d, and that's the big portion right here. So the intersection of those two functions together gives you the root. It seems it's almost, let's say, 1.5. Okay, I just plugged some values for the moments and torques to give you this. Another method is to take d from the left side to the right side, and then you have f of d equal to 0. So we're going to plot this big 1/3 portion minus d equal to 0. So we'll plot this big function, and then the intersection with y equals 0, which is the x-axis, will be my solution. And all of them are valid. So that's my f of d minus d function here. And you can see the intersection, it's right here. If you zoom this, you will have actually this. And it's almost 1.5, so it's matching with the first one. However, this is graphical. You need to plot like the function, etc., and it might be not very accurate because It depends on like the graphical method that you're using. And we want something that we can use much faster, and that's why we will be building a spreadsheet to solve that using the Newton Raphson's method. So the procedure for that is, as I've said, this is my flow chart. We will make an initial assumption. We will evaluate C size, and then we will evaluate the fatigue or endurance strength, and we will calculate d nu, and we'll look, my check for delta D is d nu, the calculated value, minus the assumed value. If delta D is less than an acceptable range, or what I call the tolerance. If it's less than that, then we will exit my, so let's say I'm doing a for loop, so I'll exit my for loop, I will stop doing the trial and errors, because my two values are very close. If not, then I'm gonna make a new assumption equal to the calculated value. I'll take it back and reevaluate my C size and keep doing this until I meet my tolerance value here. Okay. So let's take a look into this problem or example 10.1. So we're solving the values from row A, part A. So we have a shaft that's rotating and it's under a torque. It depends from case to case what kind of torque we have. So here we have a repeated torque because Tmin is 0, Tmax is 2000, and then it's under bending by this transverse load P. So it's gonna try to bend this. So we need to find the diameter if the shaft is machined and taking a 99% reliability and assuming room temperatures. Let's take the fatigue factor of safety 2, and from that example we have the ultimate tensile strength. It's equal to 108 KSI. And then we also have SY equal to 62 KSI. Alright, so the first thing is to find the maximum moment. Now this shaft is going to rotate, so at one instant it's plus here and then it fluctuates, so it's fully reversed. Moments, and you can see from here you have maximum and minimum, so it is fluctuating. However, it's a special case of fluctuation, it's repeated torque. So we have T mean in this case equal to the amplitude torque equal to T max over 2. So it's 2000 over 2, that's 1000. And the dimensions are inches for these three. The distances are in inches. This one in pound force, and these are in inch pound. For the moment, the two edges, they have 0, so the maximum moment will be at point, let's call this A, B, it would be at point B. So M at point B, if we look from the right side, we have MB, and we have the load P. So if we take counterclockwise as my positive moment, so I have minus MB, and then P is also rotating in clockwise, so it's minus P into this distance, which is B minus A. Equal to 0. B minus A is 2 inches for part A. P is 1000, so I'll get MB equal to minus 2000 inch pound. Now it's fluctuating, that means MA is equal to M max, it's 2000 inch pound, and the mean value is 0. Okay, this is fully reversed moment. Now I dropped the sign. If you look back into your equation, you can see actually the moments and the torques are actually all, each one of those, it's under square, so that's going to resolve that issue. So regardless if it's plus or minus, and again, if I flip my moments, it's gonna flip the value, and that's the maximum. So after 180 degree, this will be the minimum value. So the moment is actually fluctuating between plus and minus 2000, and that's why MA is equal to M max, which is 2000, and M mean, which is here, it's equal to 0. Okay, let's neglect, we don't have enough information to look into these stress concentration factors. So let's take Kf, all these stress concentration factors equal to 1. And next we need to calculate the corrected endurance strength. So it's the C load, C size, the surface temperature, temperature correction factor, reliability, and SE prime. Okay, so let's take a look into these tables. Okay, so first we have steel, and my SUT, we're doing English units, so it's 108 KSI, so it's below the limit, it's below the 200, so my SE prime, the M corrected value, it's 0.5 times the SUT, so it's 54 KSI. We'll go over the tables and then we'll go back. We have bending and torsion, so it's 0.577. My C size, that's the big one that gives us some issues there in my equation, and that's 0.869, since again we're doing the English units. So we'll pick this value, plug it in my SE. Next we'll use this table and equation to evaluate C surface. We have the material, it's machined, so we'll use 2.7 and negative 0.265, so we'll substitute here 2.7. Remember, SUT has to be in KSI, not PSI, so it has to be as 108 minus 0.265. And that would be 0.781. And then we have room temperature, so it's less than 450 or 840 Fahrenheit, so C temperature will be 1, and we're using 99% reliability, so we'll pick this value for the reliability correction factors. So let's take all these factors, plug them here. The only one that's not a pure number is this, it's 0.869. So we're assuming we have to double check also for the diameter once we're done if it's between 0.3 and 10 inches, otherwise I can't use this form. So d to the negative 0.097, and this actually gives me 17.21 d to the negative 0.097. Okay, so my diameter equation becomes 32 times the factor of safety divided by pi ¾ or 75, and I'm dropping the stress concentration factors because we ignoring that, so we're taking them as 1. Now here, since the moment is in inch pound, so we have to make sure that we match the units here. SE prime was 54 KSI, so this will actually gives me KSI, and this is inch pound, so to have the right units we have to say 17.21, or just let's take it as, let's leave it as SE, which is function of D, plus we don't have mean value for the moment, so it's square root of 3/4, 0.75 times the mean value for the torque divided by SUT raised to 1/3. Okay, so just make sure that when you substitute this one down here, to multiply it by 1,000 to have the right units. So how to solve it? We'll make an initial guess. That's the hard part. Make an initial guess for D. So I started with 1 inch, and then I evaluated my SE, which is 1721 KSI, so it's 17,210 PSI. We will plug it here, we'll plug all the values, and then we will find D calculated to be 1.4 inches. So my delta D1 is 1.4 minus 1, that's 0.4 inches. So it's not small enough. So now that's the trick. We'll take the new assumption, D assumed 2, to be, so that's 1, to be my calculated value. So we'll make D assumed 2. And usually if you're close enough to the solution, then it's going to converge from 2 trials. So D assumed 2, we'll take that as 1.4 inches. We'll repeat the same steps, and we'll get a calculated value equal to 1.414 inches. So you can see delta D is becoming smaller, so 0.014. So we'll take, do we need to do that just to be more and more accurate? However, it's becoming clear that it's like fluctuating or taking that, refining that answer around, this is 3, around this 1.4 answer. So now we want this to be more off. We need to build a spreadsheet to build or to calculate the diameter here. So I'll be sharing that, but before we do that, if you can input these values, and those are the correction factors for the loading, C surface. We only need actually this and this. These will depend on the SUT value, so don't enter these, we'll enter the equation. And then we have the reliability table. And then I'm going to use the two functions from Excel. One is just simply to pick a value. You don't have to do that. I'll be using the list function, so I'll be creating a drop-down list. And then I'm going to use what I call the index and match to pick the value from here, and we'll see that. But that will be part 2 of this recording. So we'll wait and we'll upload that in part 2, and we'll do that in part 2.